All right, hello class. This video lecture is going to be on measurement uncertainty, accuracy, and precision. Okay. In this course, we're going to be dealing with two types of numbers. We're going to have exact numbers and measured numbers. Okay, so let's talk about the difference between these two types of numbers. Exact numbers are just that. They're exact. There is no uncertainty, no level of uncertainty in an exact number. So here we're talking about counted numbers or defined numbers. So for example, let's suppose there are 24 students enrolled in a chemistry class. Okay, 24, that's exact. Exactly 24 students. There are exactly 60 seconds in 1 minute. Okay, so that's the definition of a minute. It's 60 seconds. So we have defined numbers. Okay, 60 seconds equals 1 minute. 1 foot is equal to 12 inches. 1 kilometer is equal to 1,000 meters. Okay, so those are exact defined numbers. And here's another very important one. Okay, 1 inch is equal to 2.54 centimeters. That is by definition. That is an exact number. Okay, so in the previous video lecture, we were talking about the SI prefixes, and I told you you would need to learn all of those SI prefixes. The only English to metric conversion factor that I will want you to learn is this one right here. Okay, 1 inch is equal to 2.54 centimeters. That is exact. Okay, so we need to learn those SI prefixes, and we do need to learn this. So these are all examples here of exact numbers. Okay, well, what about measured numbers? Okay, measured numbers have some level of uncertainty. Okay, there is always a certain amount of error in a measured number. They cannot be known exactly. Okay, there have to be estimations that are made. Okay, anytime someone is making a measurement, estimations must be made. Okay, now, one very important thing that we need to remember, especially in lab, when we get into lab and we start making measurements, a measurement consists of two things, a number and a unit. Okay, we never want to write down a number without a unit. Okay, so that's going to be very important to include numbers and units in our measurements. Okay, so let's talk a little bit about measured numbers. Okay, so for an example here, let's consider measuring the volume of water in a graduated cylinder. Okay, so this is a diagram here, a figure from your textbook. Imagine that we have a graduated cylinder and there is some water in it. Okay, now we're going to kind of expand on this section right here. Now, each one of these little divisions on the graduated cylinder represents a milliliter. Okay, we've got 5, 6, 7, 8, 9, 10, and so forth. Each division represents a milliliter. Well, if we kind of, magnify this, blow this up a little bit, we can see that the level of liquid, this is water in here in the graduated cylinder, it's between 21 and 22 milliliters. Okay, now, this forms what we call a meniscus. Okay, this is a concave meniscus. And anytime you read, water in a graduated cylinder, you read the very bottom of the meniscus. So if you look at this right here, you'll see that this is a little bit more than halfway. This is 21, this is 22 milliliters. It's a little bit more than 21 and a half. This is more than halfway between these two. So what we would do then is we would need to estimate where it is. And the guideline that we kind of follow is that if the smallest division is a milliliter, then we estimate to the nearest tenth of a milliliter. Okay? So we said this is a little bit more than, halfway. If it were halfway between 21 and 22, we would say 21.5. It's a little bit more than that. So maybe we might look at that and say, I estimate that that's 21.6 milliliters. Or you might look at that and say, I think it's 21.7, milliliters. I'm sorry. We're talking milliliters, not millimeters. So 21.6 or 21.7 milliliters. Okay. Now, when we talk about the concept of significant figures or significant digits in measured numbers, significant figures or significant digits are all of the digits that are known for certain plus one more that we estimate. Okay, all that are known for certain plus one more that we estimate. So if we had looked at that volume and said we think it's 21.6 or 21.7, we would be certain of the 21. We knew that it was between 21 and 22. So these two digits we know for sure. This is our estimate, okay? Or this is our estimate. Which one of these is right? Well, either one of them is right. I mean, they're both right. I might look at that and say, I estimate that it's 21.6. You might look at that and say, well, I think it's 21.7. So this is kind of our best guess, okay? So when we're trying to make these estimations or guesses, we do want it to be a good guess, a good estimate. We don't want it to just be a wild guess, okay, or something that's not very good. In other words, we wouldn't want to look at this and say, I think that's 21.5, because if you look at this, it is more than halfway. So 21.5 would not be a good guess. 21.8 probably wouldn't be a good guess either, because, it would be a little bit higher if it were 21.8. So one of the aspects of making an estimate is it needs to be a good estimate, okay? So we could say 21.6. Now, would it be appropriate to say 21.60? Okay. I mean, when you look at this number, 21.6, and you look at this number, 21.60, in terms of making guesses, those are different numbers, okay? So we would not want to say 21.60. That would not be correct, okay? Remember what the guideline is, okay? This is a very important sentence right here. When making measurements, always estimate one decimal place past the smallest division on the instrument. Okay, so the first thing you want to do is you want to find the smallest division on the instrument, and then you want to estimate one decimal place past that, okay, when you're making a measurement, okay? So let's look at another example. What if we had a thermometer? Suppose we have a thermometer, we're measuring the temperature of a liquid or a solid, some sample, okay? So we're going to kind of show, I'm going to try to show a blow up of this section right here. So suppose this looks something like this, okay? So we got 88, 89, 90, 91, 92. Okay, so each one of these divisions represents a degree. Okay. Now, it looks like it's right on the 92. Okay. 92 degrees Celsius. Okay. So, well, look at what we said right here. Look at what's in bold. We always estimate one decimal place past the smallest division. Okay. So what do you think we would say here? Would we say 92 degrees, 92.0 degrees, or 92.00 degrees? Okay. Well, since the smallest division is 1 degree Celsius, we want to estimate 1 decimal place past that. We would have to estimate to the nearest tenth of a degree. Okay, so the 92.0 degrees would be correct. Both of the others would be incorrect, okay? So it's very important. We're going to, I mean, you might look at this and say, you know, mathematically, these are all 92. What's the big deal? Well, it's going to be a really big deal because what we often see, class, is we make measurements in the lab, but we end up doing calculations with those measurements. Okay, so if there is some uncertainty in the numbers that we're measuring, there is going to be some level of uncertainty in the calculations. Okay, so we have to be able to deal with that. So if you will, you know, make note of this sentence right here. This is going to be very important, and we're going to get some practice at this in laboratory. Many of the instruments that we're going to be using are going to be what we call analog instruments, okay, where you have to kind of make a guess. Now, some of the instruments that we're going to be using are digital instruments, okay? So let's look at that. What if we have a digital instrument? Okay? So this is an example here. This is a balance. We've got a container, we've got a sample in the container, and we've got a mass here that's displayed on the balance. Well, this is the guideline for digital instruments. All of the digits displayed on a digital instrument are significant. Okay? All of the digits are significant. So in this example right here, we've got a combined mass of the container and sample of 111.77 grams. Okay? There are 5 significant figures in this. Okay? So all of these are significant. Have you ever, I mean, I know you have all used digital instruments. You've either used a digital thermometer, or maybe you've, you know, gone to visit the doctor, and, you know, and they tell you to step on the scale, and you're standing there, and or you're massing something, and you notice that there's some fluctuation in this very last digit. So this might read 111.77, 78, 77, 78, and it kind of fluctuates, and then it stops. That's the instrument making its best guess as to what that last digit is. Okay, so these are the digits. These first 4 digits are known for certain. This last one is the one that's estimated. So it still kind of follows the same guidelines. Significant figures are all the ones that are known for certain, plus one more that is estimated. Okay? All right. So there are certain guidelines that we have for significant figures. Okay? When you're making a measurement, we're going to be getting some practice in lab, and you will learn how to estimate your answers to the correct number of significant digits or significant figures. But what if you're not in the lab? What if you're just encountering a number, maybe in a problem that you're working from the textbook, or you just encounter a number? How do we know if it's significant or not? Well, these guidelines, this is all in your lab manual, class, what we're talking about here. It's also in your book. Let's kind of go over the guidelines and let me show you some examples. Okay. All non-zero digits are significant. Okay. So if we have the number 235, all of these are going to be significant. So a lot of times we'll abbreviate significant figures. We'll call those sig figs. Okay, so we've got 3 significant figures in 235. 24.86, those are all non-zero digits. All 4 of those would be significant. Okay. So all non-zero digits are significant. Number 2, leading zeros are never significant. Okay, leading zeros. So if I have 0.567, okay, the 5, 6, and 7 are significant, but that's a leading zero. It's not significant. So that number has 3 significant figures. Okay, if we have this number, 0.000027, this only has 2 significant figures. Okay, these 2 digits are significant. These are leading zeros. They're not significant. Okay, now class, that doesn't mean they're not important. That doesn't mean they don't serve a purpose. They are placeholders, but they're simply not what we define as being significant digits, okay, or significant figures. Okay, if we have this number here, 425.8, that's going to have 4 significant figures. Okay, so those are some examples there employing guideline number 2. Number 3, zeros between non-zero digits are significant. Okay, zeros between non-zero digits. So here, we know the 7, the 4, and the 2 are significant. That 0 is going to be significant. So we've got 4 sig figs there. If we have this number right here, we know the 3 and the 4 are significant. These are leading zeros. What do we say about leading zeros? They're not significant. But here's a 0 that's between 2 non-zero digits, so it's going to be significant. So we're going to have 3 significant figures in this number. Okay, 2,305. Okay, all 4 of those are going to be significant. Okay, so zeros between non-zero digits are significant. Okay, all right. Trailing zeros are significant if the number contains a decimal point. Okay, if the number contains a decimal point. So let's look at some examples there. 4.60. Okay, so we know the 4 and the 6 are significant. That's a trailing zero. There's a decimal, so it's going to be significant. 3 significant figures there. Okay, let's say we've got this one. The 7, the 3, and the 2 are significant for sure. Leading zeros are not significant. Trailing zeros are significant if there's a decimal. Okay, so we're going to have 4 significant figures in this number. Okay, and then we're going to look at one more example, or a couple of more examples here. 200. Okay, so look at this. This number is written in this way, 200, but there's a decimal there. So we know the 2 is significant. Both of these right here, these are trailing zeros. There is a decimal in that number, so all 3 of those are significant. Okay. What about this number, 200, written like this? Okay, the 2 is significant. These 3 zeros are trailing zeros. Since there is a decimal, those are going to be significant also. So 4 significant figures. Okay. All right. Now, number 5, trailing zeros are ambiguous if the number contains no decimal point. Okay. So if we see a number written like this, 80, okay, we know that 8 is significant, but we don't know if that 0 is. Okay, ambiguous, we can't tell if that's significant or not. So we know this number has 1, maybe 2 sig figs. Okay, if we have the number 2100, okay, we know the 2 and the 1 are significant, but those trailing zeros we don't know. So we've either got 2, 3, or 4 significant figures. Okay, so how do we avoid the ambiguity? Okay, we write the number in scientific notation. To avoid this scenario where, we don't know if these trailing zeros are significant or not, we write the number in scientific notation. So if we go back to this 80, if this number has one significant figure, we would want to write it like this: 8 times 10 to the first. One significant digit, one significant figure. If it has two significant figures, we would want to write it like this. Okay, 8.0 times 10 to the first. Notice, class, when we write a number in scientific notation or exponential notation, this number right here, this is called the coefficient. And this is the power right here. So when you write a number in scientific notation, all of the digits in the coefficient are significant. Okay, because now we've written it in such a form that it appears to be a trailing zero and there's a decimal, right? So let's come over here to this. We know the 2 and the 1 are significant. If this number is supposed to have two significant figures, we would want to write it like this. Okay. If it has 3 significant figures, we would want to write it like this. And if it has 4 significant figures, we would want to write it like this. Okay. Now, I know there are some of you, many of you maybe, looking at this saying, you know what? Mathematically, these are all the same thing. This is 2100. What difference does it make? Okay. It makes a lot of difference, okay? We're not talking about exact numbers here. We're talking about measured numbers, okay? I'm gonna show you some examples in the next lecture when we start doing calculations with these numbers, why this is a big deal, okay? So we need to get some practice with this. There are several practice problems. This is all talked about in your lab manual, in the first few pages of your lab manual, as well as your textbook, okay? So we're going to get some practice with this. All right, the last thing I want to touch on here are the terms accuracy and precision, okay? These do not mean the same thing, okay? Many times they're used interchangeably. They do not mean the same thing. Accuracy refers to how close a measured value is to the true or actual value, okay? Whereas precision refers to the reproducibility of a measurement, okay? If you're making repeated measurements, how close are those repeated measurements to each other, okay? So accuracy and precision, they do not mean the same thing. Let me kind of show you an example. There's an example in your book that I kind of wanted to go over, okay? So imagine that we have 3 people throwing darts at a dartboard, okay? So we've got 3 people, A, B, and C, and we've got this person throwing 3 darts, this person throwing 3 darts, and this one throwing 3 darts. So let's take a look at this. What are we trying to do? We're trying to hit the bullseye, right? We're trying to hit in the very center. So if we look at this first dartboard here, this is very accurate and precise. Okay, so what do we mean? Accurate, they all hit the bullseye. That's what we're trying to hit, the bullseye. So very accurate and precise. What does that mean? They're close to each other. Okay? So accurate and precise. That's really what we would like to have in the lab when we're making measurements. Okay, so let's look at this here. Okay, did these hit the bullseye? No, they came close, but they didn't hit the bullseye. So what can we say here? These were precise, but not accurate. Okay, they were close together. They were close to each other. The precision is very good, but the accuracy was not good. Okay, so we can have instances where we are precise but not accurate in the lab. I mean, we want to try to avoid that. We want to be accurate, but This is possible here. Look at this third case over here. So this person throwing these 3 darts, not accurate, and what? Not precise. Okay? So we really want to try to avoid this. So this is really what we would like. We would like to be accurate and precise. We would like for our measurements to be reproducible. Okay? So your lab technique is going to determine how accurate and precise you happen to be. Okay? All right. So that concludes this video lecture. Again, this material is in Chapter 1 in your book, Significant Figures, Uncertainty in Measurements. That's also discussed in your lab manual as well.